Hey everybody, we're here today talking about graphs of polynomial functions, how to analyze them, and what the important features are. So let's take a look at the first example. Go ahead and pause the video, take a look. What do you notice? What do you wonder? And when you're ready, proceed. So you've had a chance. You're going to notice lots of things. Here's what I notice. The highest degree of any of the expressions is degree 3. So this is a degree 3 polynomial. Okay, quadratic always being a second degree. Now, we're going to notice that there's x-intercepts. This one's close to 4, not quite 4. We'll take a look at that in a sec. We have a y-intercept right here, and that's actually going to be -2. Okay, if we plug in 0, everything disappears, right? Here's our y-intercept, just like before. Our constant term is the y-intercept. And then we have a maximum here and a minimum down here. So these are both called, they're local, okay? The values actually keep getting bigger as we travel to the right. Okay, as x goes to infinity, y also goes to infinity. They get larger, right? So there is no overall maximum. Okay, so this value right here, okay, that max that's there is called a local max. The same thing is true right here. It's called a local min because it's a minimum value here, and there is no global minimum because as we travel to the left, our graph goes down, right? Which means that as x goes to -infinity to the left, y is going down, okay, to -infinity as well. Okay, there's a portion right here where it's concave down, and a portion right here where it's concave up. All right, so we can have multiple types of concavity in a higher degree polynomial. Right? Now, if we go and take a look at Desmos, see what we got going on here. Okay, here's our standard viewing window, same graph that we were looking at. When we click on it, we actually pops up the different things. So here's our x-intercept. It is not quite 4. Okay, the value is actually 31/8. It's close, but not quite. Here's our minimum. Okay, again, an approximation, our maximum, and our y-intercept. Okay, so Desmos will provide all those things readily. Okay, again, approximations, just like calculators do. You're going to need calculus to find these max and mins by hand. Okay. So the next example, take a second, pause it. What do you notice? What do you wonder? So hopefully you remember back to quadratics, right? This is going to be factored form, and we've got 3 different factors. When we multiply these together, it's actually going to give us a degree 3 polynomial. Okay, so it's a third degree just like the last one, but something's changed. The leading coefficient is negative this time, and we can see that there's been this reflection in the end behavior. Okay, now it's going up and to the left and down and to the right, right? So as x goes to positive infinity to the right, the y values are getting smaller. They're going down to -infinity. And as x goes to -infinity in the other direction, the y values are getting bigger. Okay, so this is the opposite of the last problem. Okay, same degree, leading coefficient's negative, so that changed things. Right, we still have this max and a min. Okay, our minimum's over here, our maximum's over here. This minimum, the area above it is concave up, and the area below the max is concave down. Okay, somewhere in between there's this point called an inflection point. Again, you can find that using calculus. Right, now our zeros. Well, we've got a 0 at -5, 0, and 3, and those are going to correspond with the zeros of the equation, just like we saw with the quadratic. Okay, so this factored form already told us what the zeros were. We can see it mirrored here. The y-intercept in this case is actually 0, okay, and that's because x equals 0 is a 0 already. In the next example, take a second, pause the video. What do you notice? What do you wonder? So hopefully you notice that we're looking at an even degree this time. Now it's a degree 4 polynomial. Okay. We can only see there's only 3 terms here, but that's okay. We don't need a cubic term or a linear term. We can still know that the y-intercept is actually this value right here. Okay, it's hard to tell by looking at the graph, right, that that's a fraction. Okay, that's somewhere in between 60 and 70, right? Our zeros, looks like negative 20, negative 10, 10, and positive 20. And then we have a couple local minimums down here, okay, close to negative 30, right? Our end behavior, it doesn't matter which direction we go. As x goes to negative infinity, y is getting larger towards infinity, and when an x goes to positive infinity to the right, y is going up to positive infinity. Okay, so this is similar to quadratic with a positive leading coefficient. We also have concave down below the max, concave up above the mins, okay, and there's inflection points somewhere in between. All right, take a look at the last one. What do you notice? What do you wonder? So hopefully you've noticed the factored form, and this time we have multiple of the same factors, right? X equals negative 6 is a 0, but it's a 0 twice because there's two factors that go with it. And then x equals 0 is a 0 3 times. Okay? And x equals 5 is a 0 1 time. And we can see all of that in our graph. Now, it might not be apparent, but the fact that this at x equals negative 6, that it touches the x-axis, that's important. We have a multiplicity of an even number here, so it touches the x-axis. When we have a multiplicity of an odd number, it actually goes through the x-axis. Okay, so even though there's a total of, let's see, 6 zeros, okay, there's only 3 x-intercepts. Right? There's maximums and minimums around. Okay, in this case, this is a global max because it is the highest point of the graph overall. And similar to the last one, we can see that the graph is going in the same direction, the y on the end behavior. Okay, as x goes to negative infinity, or as x goes to positive infinity, right? The y values are getting going down towards negative infinity. Okay, right? And again, this is similar to a quadratic because we see we have a negative leading coefficient, right? So it opens down, and we have an even degree of degree 6 because we have 6 total factors here. Okay, so when we multiply that out, we'd get a 6-degree polynomial. Okay. Again, we got different concavities. Here's concave down, up. This portion actually is going to be concave down. Okay, it actually does not change. Okay, it stays concave down here. It actually is concave up here and then concave down here. Okay, there's lots of concavity changes here. Again, some calculus would help see what's going on there. So overall, we got a lot going on here. We've got intercepts. Our y-intercepts hasn't changed. We can just plug in x equals 0. For our x-intercepts, y is 0. We might be able to find it if it's in factored form by using the zero product property, or we might have to factor it or use a calculator. For extrema, we've now got multiple types of extrema. Before it was just one extrema, either a max or a min. Now we can have local extrema, which are maximums or minimums within a particular area, or global extrema, which is the largest max or largest min of the overall function. And then end behavior. End behavior, again, I want to think about this just like we think about the two most basic polynomials. The most basic odd degree polynomial is a line. The most basic even degree polynomial is a quadratic, okay, a parabola. Okay, so I want to think about those graphs when we think about end behavior. For odd, we saw that when the leading coefficient was positive, okay, just like when a slope is positive, it's going up and to the right and down and to the left. When the leading coefficient was negative, that changed. Okay, again, just like with a line. Negative slope, it goes up and to the left and down and to the right. For an even degree polynomial, it's like a parabola. With a positive leading coefficient, it opens up. So both the ends go to positive infinity, and when it's got a negative leading coefficient, it opens down. Okay, whatever's happening in between, Okay, there's lots of variety, lots of things can change, but overall it's going to be like a line or a parabola. So go try the practice out and come to Zoom office hours if you have any questions. Good luck.